Now it's time to get down to the business that we love most, mathematics. I'd like to talk about some work that I did a long time ago. Somehow nobody has noticed it very much. And I do believe it's one of my favorite pieces of research. It has a nice Scandinavian title, abstract version of the Phragmen-Lindelöf principle, and it's also an abstract version of Saint Venant's principle, who was not a saint but a French mathematician. And I will start with a concrete example and then state and prove a vast generalization of it. So in the concrete setting, we have a half strip. X goes between minus pi and half and plus pi half, and y goes from 0 to infinity. We have harmonic functions h of xy, which are, number one, bounded in this strip, and number two, vanish on the vertical boundaries. And a Saint Venant-like principle is that such a harmonic function has an expansion in terms of these exponential solutions of this problem. And by asymptotic expansion, I mean asymptotic in the sense of Poincaré, that the difference between the function and the first n terms decays like the next term, or very nearly like the next term. So I give now the proof. It works. I need first a lemma which says that such a harmonic function, which was only assumed to be bounded, actually decays exponentially. And the proof is very cute. It's based on the maximum modulus principle. And I compare the function h of xy to another harmonic function, both of which are exponential in y and cosine in x. The first term decays exponentially, the second one increases exponentially. Now, I say that the harmonic function on the right-hand side is greater than h on all four sides of a rectangle formed by the vertical sides, the side y equals 0, and the side y equals capital Y, where capital Y has to be taken large. Why is that so? Well, on the vertical sides, obviously h is 0, and the right side is positive. Initially, I chose m prime so that the first term is greater than m initially. And finally, on the top side, y equals capital Y, it's the second term that kicks in. No matter how small epsilon is, eventually the increasing exponential function in y will overwhelm anything. And so we have the inequality on all four sides. Then by the maximum principle, it holds also on the inside. And we get a similar estimate from below. And then, since this holds for all epsilon, it holds for epsilon equal to 0, QED. The rest of the argument is functional analysis. the space of harmonic functions that I have defined before forms a Banach space in the maximum norm, and translation maps this space into itself. S has to be positive, of course, and now the proof of the assertion is based on the fact that translation is a compact operator. Sorry. What does it mean that it's a compact operator? One has to show that the image of the unit ball is pre-compact. Well, that follows from the fact that harmonic functions are very smooth in the interior, and boundary points where boundary conditions are satisfied count as interior points. You can, for instance, continue the function by reflection. And the only non-interior part, which is at near y equals 0, has been shifted out. So on any compact portion of the half slab, these functions are compact in every sense. All their derivatives are bounded. So to conclude that they are pre-compact in the whole half slab, we use the fact that they decay exponentially at infinity. And that's it. Now, there's a very beautiful theory of compact operators in Banach space due to Frederick Ries, 1915. He showed that such an operator has a discrete spectrum. Now, the translations form a semigroup. So if you have, and they commute, and therefore they have common set of eigenfunctions, as I've written over there. Very easy to see that the eigenvalues themselves depend exponentially on S, and so do the eigenfunctions, as I've written in the last line. And the eigenvalues all have to be less than 1, so that means the mu has to have a real part negative. So the last step is, and this is just the eigenvalue equation. Now the last step is based on the formula for spectral radius. You take an arbitrary harmonic function. Capital Pj is projection on the jth eigenspace. And so every h in this Banach space can be decomposed into a finite sum of the first n eigenfunctions, Pj of h, and the remainder. Now the remainder belongs to the Banach space H sub n, which is the same space except the projections of these functions onto the first n eigenspaces is 0. Now the spectrum of translation acting on H sub n is the same as the spectrum before, except that the first n have been cut out. So there are the eigenvalues. Now, the formula on spectral radius says that the norm of T sub n to the power k and take the case root, not the case power, sorry, that's the spectral radius, and the spectral radius is the remaining eigenfunction. And that's the end of the proof. Okay, so now in the 50s, there was an outburst of studying general elliptic partial differential equations, and so it was natural to try to generalize it. Specific instances, of course, were known: biharmonic equation, equations of elasticity. I wanted to do something in general, and of course I realized that maximum principle is very special for the Laplace operator. One has energy principles for more general elliptic equations, but it occurred to me to give up entirely differential equations and rely only on the intrinsic properties of solutions of such equations. And the overarching property of solutions of elliptic equations is that they are very smooth in the interior, in contrast to hyperbolic equations, which can carry discontinuities. And this is true even at boundary points, provided that the boundary conditions are coercive. So I call this property interior compact. And so here's the abstract setup. Instead of considering functions in a half cylinder, I consider functions on the positive axis, y greater or equal to 0, but the values of functions are vector value. They belong to some Banach space, and they have the following two properties. They are translation invariant, which in the concrete case means that the coefficients of the equation from which they came should be independent of y, and ditto for the boundary conditions. And the second thing is this property of solutions of elliptic equations, which I call interior compact, and is the following. Define the AB norm to be the L1 norm over the subinterval AB. A and B are both positive. And then I require that the unit ball in the AB norm should be pre-compact in the A prime B prime norm, where A prime B prime is a subinterval of AB. So H is defined as the set of all U in this space which are integrable from 0 to infinity. If it's not complete in that norm, just complete it in that norm, and you do not lose the property of interior compactness. So, and the main theorem that I want to prove or sketch the proof of is that the translation operators, which again form a semigroup, these operators are compact. And once you have that result, you can argue as before using Frederick Ries's theorem. You have discrete spectrum. There's an asymptotic description. Now, remember in the specific case, there were two elements to proving the compactness of T of S. One was compactness over pre-compactness over finite portions of the cylinder, or in this case interval, and secondly the uniform exponential decay at infinity. Now here, the first element, compactness over finite intervals, is part of the hypothesis. And the amusing thing, that's why I like this result, is that the second property, exponential decay, follows from the first property. You don't need maximum principle, and it's a very cute argument. So here is the auxiliary theorem. That if function u is integrable from 0 to infinity, then it in fact decays exponentially in the sense that there is a positive constant c, that u is integrable even with an increasing exponential factor in it. And then by principle of uniform boundedness, it follows that the integral with the exponential factor is bounded by a constant times just the L1 norm. Now, the proof of it is tricky, but the tricks are amusing, and therefore I would like to present some of them. First of all, the translation operation is a contraction, so you know that its spectrum must lie in the unit disk. Now, but of course, a priori it could be the whole unit disk. So I have a series of lemmas which chip away at the unit disk, showing that not all of it can be the spectrum. So the first lemma says that for S small enough, -1 is not in the spectrum of T of S. The proof goes by contradiction. Suppose that -1 is a point of the spectrum of T of S. Then it certainly is a boundary point of the spectrum, because everything outside the unit disk is in the resolvent set. And then, since the norm of the resolvent tends to infinity as you approach the spectrum, it follows that there exists a sequence of elements un in H of unit norms, so that when Ts plus 1 acts on un, the norm of that tends to 0. So, or so that the ratio of those two norms tends to 0, is less than epsilon n. So I write the norm is an L1 norm, so it can be written as sum of L1 norms over the unit intervals k to k plus 1. And if you have numerator is a sum, the denominator is a sum, and the ratio is less than epsilon, and then there must be some k for which the ratio is less than epsilon n. So then I shift these. Instead of having functions between k and k plus 1, I have functions between 0 and 1. That's just a shift downward, and I renormalize them so that the norm 0, 1 norm of un is 1, and the 0, 1 norm of un plus tun is less than epsilon n. So then, from these two, I conclude that the norm of un from 0 to 1 plus s is less than 2 plus epsilon n, because un and tun differ by less than epsilon n. So then by interior compactness, I conclude that these un's subsequence is convergent, and I call the limit u, and the limit will satisfy the equation that u plus ts of u is 0, which means that u alternates on intervals of length s. Now, if there were such functions for all s, we would have a sequence of functions that are bounded in the norm 0, 1, but not compact in any subinterval, because they just alternate in sign. So that contradicts the assumption of interior compactness, and follows that the assumption we made is erroneous. That is, there is some value of s for which -1 is not in the spectrum. Now, from this point, we can analyze the spectrum and prove, this is another auxiliary theorem, that the spectrum in fact is a discrete subset of the unit disk accumulating in the open unit disk and accumulating only at 0. Now, how do we do that? Well, we argue with, since we know that not the whole unit disk is the spectrum, we know that there must be points of the spectrum inside the unit disk which are boundary points of the spectrum. And then it follows again as before that there is a sequence u sub n of functions of unit norm for which t minus lambda un tends to 0 in norm. Now, I claim that a subsequence of this u sub n converges to an eigenfunction of t with eigenvalue lambda. Now, again, there's no difficulty with any, since the norm of un over interval 0 to infinity is bounded, we know that in any subinterval S capital T, there is a convergent subsequence. And so, but to show convergence in the norm 0 to infinity, we need something about the, you see, it could very easily happen from this argument that in any interval 0 to t, this limit is 0. So I could be left with nothing. So I have to show that actually these converge in the L1 norm over the whole interval 0 to infinity, and since they are unit norms, the limit 2 would be a unit norm. And to do that, we have to show that these functions u sub n are uniformly small at infinity. And this I will get out of the eigenvalue inequality. So I start with the identity that the difference of t to the m minus lambda to the m can be written, well, this is high school identity. And I apply this to the function u sub n, and I look at, now remember I want to show that the un's are uniformly small at infinity, which is equivalent to saying that as m tends to infinity, t to the m un tends to 0 uniformly. Well, I estimate the right side. The first term has a lambda to the m minute. Lambda is in absolute value less than 1, so it tends to 0. And in the second term, I have t minus lambda un, whose norm is less than 0. The norm of capital T is at most 1, and these lambdas do no harm, in fact help. So the right side tends to 0 uniformly, and that proves my contention. And it shows that the null space of T minus lambda is not empty. Now, I want to show that lambda is actually in the point spectrum, which certainly means that the null space of T minus lambda is not empty, but I want it to be finite dimensional. Well, that also follows very nicely from interior compactness, because the norm of u from 0 to 3s, since u is an eigenfunction of T of s, is equal to its norm from s to 2s, because it's just repetition of itself over the 3 subintervals 0 to s, s to 2s, 2s to 3s. So the 0 to 3s norm and the s to 2s norm are equivalent. Now, by interior compactness, the unit ball in the 0,3s norm is compact in the S2s norm, which is the same norm. So, by another theorem of F-Rees, the unit ball in N is finite dimensional. Okay, now that's not all that we need to place lambda squarely in the point spectrum. We also want to look at the generalized eigenfunctions, which is the null space of T minus lambda to the square, cube, etc., and to show that after a finite number of steps, they cease to increase. Now, what we know about these dimensions is that the difference, that the dimension of nk plus 1 over nk is a decreasing sequence. That's because T minus lambda maps the quotient space nk plus 1 in a one-to-one fashion onto nk quotient by nk minus 1. So the dimensions must decrease. And so we have a decreasing sequence of integers. And then it follows that from a certain point on, these dimensions must all be equal. I was particularly pleased by this, by the non-constructiveness of this argument. I am not a constructivist, and it pleases me to tease my constructivist friends. But when I feel constructive, I do numerical calculations, but when it comes to abstract arguments, I accept anything. And so, and here there are a couple of tricky lemmas. I look at the union of all these n's, and I show that T minus lambda maps the quotient space of H divided by the closure of this space. one-to-one onto itself, and from that one can get, it's not hard to show that there is a value I from which these subspaces stop increasing, and then one deduces easily that this lambda is an isolated point of the spectrum. Well, now remember, this was a statement about the boundary points of the spectrum, but from it follows very easily that the spectrum has no interior points, because if there were an interior point mu of the spectrum, we could connect it to -1 by a straight line. Well, we shouldn't go through lambda equals 0, so we accept the break in this line. And then there is a point lambda such that all points between lambda and mu belong to the interior, but lambda does not. And then we have readily a contradiction, because this lambda is then a boundary point of the spectrum and therefore isolated. And therefore it could not be true that between lambda and mu all points are in the spectrum. So from this it follows that all points in the spectrum, in the interior of the unit disk, all points of the spectrum are isolated, and the spectrum could accumulate only at 0 or possibly on the unit circle absolute lambda equals 1. Now, when lambda is on the unit circle and in the spectrum of T, we have constructed an eigenfunction. We constructed it only on a finite interval that can easily extend it to the whole interval. This eigenfunction does not belong to the, cannot be integrable, so doesn't belong to the space H. But now, let me show by a simple argument that in fact the unit circle cannot be a point of accumulation of the spectrum. It's a very simple argument and goes as follows. I construct a new space, S sub p, which consists of functions in my old interior compact space S multiplied by an exponential function. It follows easily that this new space S sub p is again interior compact, because on finite sections of the y-axis this factor doesn't matter, and it's again translation invariant because the exponential function is, and therefore it the same result that I have deduced before applies to this new space. And if I take the integrable functions belonging to S, then if lambda is in the spectrum of translation over S, then e to the minus p lambda is in the spectrum of translation over the over H sub p, and that shows that the spectrum could not have accumulated on the unit circle, because over H sub p it would accumulate inside. So now, so the last step is to prove that in fact the unit circle contains no point of the spectrum, and I proceed as follows. I choose P so that the spectrum of translation over H sub P has no point on the unit circle. There can be only a discrete set of P's for which for which there is a point on the unit circle. And then I apply the argument that I used for harmonic functions, which is quite general, to say that every function in H sub p has an asymptotic expansion in terms of eigenfunctions, which are exponential functions of y, or polynomial times exponential functions of y. And then by multiplying back by e to the py, I get a similar asymptotic expansion for the functions u in my original space H. And I think that's the last slide. And so, by purely abstract reasoning, one can get a now Saint Venant's principle is that such an asymptotic function at infinity exists. The calculation of the coefficients is another matter, and it can be quite tricky even for a very simple case of the biharmonic equation or elasticity, but just when it comes to exponential decay and asymptotic expansion, the proof that I outlined is sufficient. I've put in a chapter, let me put in a plug to my book on functional analysis. I've put in a chapter containing this material there. And so thank you very much for listening.